Welcome to Turbomachinery. Welcome to Chapter 14 of Fluid Mechanics 2. Turbomachinery enters the dynamic world of machines that extract or add energy from a fluid through rotating components, turbines, compressors, fans, and pumps. These are not just machines. They are the heartbeat of power generation, aircraft engines, and water supply systems. Turbomachinery links theory to real-world applications. It is where control volume analysis meets rotating blades, where energy conversion becomes kinetic and mechanical motion. Today, we move beyond static systems and dive into rotating flows, torque generation, angular momentum, and the critical design parameters that shape real machines. This chapter will empower you to understand not only how turbomachines work, but why their design is so crucial to performance. You'll explore Euler's turbine equation, velocity triangles, and efficiency metrics that engineers use daily in power plants, jet engines, and hydraulic systems. Let's begin our journey into turbomachinery, the rotating engine of modern civilization.
1. Introduction to turbomachinery. Turbomachinery is the art of transferring energy between a fluid and a rotating shaft. It's where mechanical engineering meets motion, fluid motion and rotor motion working together to produce useful work. The key idea here is energy exchange, either adding energy to the fluid or extracting it. When we use a pump, we are doing work on the fluid, adding energy to move it against pressure. On the other hand, turbines are the reverse. They harness the fluid's energy to spin a shaft, generating useful mechanical power. Unlike devices that rely on high-speed fluid jets or velocity increases, turbomachines mainly operate through pressure changes. That's the essence of what differentiates them from jet propulsion or momentum-based systems. This chapter will guide you to understand how energy transfer happens in these machines and how pressure becomes the central variable in their operation. 2. Classification. Let's begin by organizing the vast world of turbomachinery into two fundamental types. The first are pumps. These are energy-absorbing machines. They do work on the fluid, increasing its energy, typically in the form of pressure or potential energy. Think of a water pump lifting fluid to a higher elevation or pressure. The second type are turbines. These are energy-producing machines. They extract energy from a moving fluid and convert it into mechanical work, usually in the form of rotating shafts, like in hydroelectric dams or steam power plants. Now let's break pumps down further. Not all pumps are created equal. Fans produce a small pressure rise but deliver high flow rates, ideal for ventilation systems. Blowers take it a step further, generating moderate pressure rises while still maintaining relatively high flow. Compressors, however, are the heavy lifters in this family. They deliver very high pressure increases, often needed in gas turbines, refrigeration, and air compression systems. Understanding these classifications is not just about memorization. It's about recognizing what each machine is designed to do and choosing the right one for the job.
3. Performance parameters. When analyzing a turbomachine, it's essential to define how well it performs. The first fundamental parameter is the volume flow rate, denoted as V dot, which tells us how much fluid passes through the machine per unit time. It's calculated by dividing the mass flow rate by the fluid density. This gives us a clear measure of the system's capacity. Next, we introduce the concept of net head, H. This represents the total energy added to the fluid by the pump. It combines three forms of energy difference: pressure head, velocity head, and elevation head. Mathematically, it expresses the combined effects of pressure rise, velocity change, and elevation gain as the fluid moves from inlet to outlet. Water horsepower is the useful output. It's the actual energy transferred to the fluid, calculated as the product of fluid density, gravity, flow rate, and head. This is what the pump is accomplishing from the fluid's perspective. Brake horsepower, on the other hand, is the energy input required to drive the pump shaft. This is usually measured at the motor and accounts for mechanical losses. Efficiency ties it all together. It is the ratio of the water horsepower to the brake horsepower. It reflects how much of the input energy actually ends up boosting the fluid's energy. A higher efficiency means less energy wasted and better performance. These parameters together define the real-world behavior of turbomachinery and guide engineers in selecting, sizing, and evaluating performance.
4. Pump performance curves. To understand how a pump truly behaves in real-world conditions, we rely on performance curves. These curves are more than just plots, they are diagnostic tools that reveal how head, efficiency, and brake horsepower vary with volume flow rate. By reading these curves, we unlock the behavior of the pump across a range of operating conditions. The most critical point on the performance curve is the best efficiency point, or BEP. This is where the pump runs most efficiently, where energy losses are minimized, and where the machine performs at its peak. Operating at or near BEP ensures reliability, energy savings, and longevity of the system. But performance is not determined by the pump alone. Every system has its own set of requirements, represented by the system curve. This curve expresses how much head is needed for a given flow rate based on system characteristics such as friction and elevation changes. The true operating point of the pump is found where the pump curve intersects the system curve. That's the point where the system will naturally settle, whether it's optimal or not. Understanding and analyzing pump performance curves is a foundational skill for selecting the right pump, diagnosing system inefficiencies, and improving operational control.
5. Pump cavitation. Cavitation is one of the most damaging phenomena that can occur in turbomachinery. It begins silently when the local fluid pressure drops below the vapor pressure of the liquid. At that moment, vapor bubbles form within the flow. But the real danger comes when these bubbles collapse violently in higher pressure regions, sending shock waves that erode metal surfaces, damage blades, and reduce the pump's lifespan. To prevent this, engineers use a critical concept called net positive suction head, or NPSH. It's a measure of how much pressure is available at the pump inlet compared to the vapor pressure. If NPSH is too low, cavitation will occur. The equation for NPSH combines the pressure head and velocity head at the inlet and subtracts the vapor pressure head. It reminds us that both pressure and velocity at the inlet affect the risk of cavitation. Higher inlet velocities reduce NPSH, increasing the risk. So too does a higher vapor pressure, which rises with fluid temperature. Avoiding cavitation is not just about protecting equipment, it's about preserving efficiency, safety, and reliability in any fluid system. Always check your NPSH. It's your first line of defense. 6. Pumps in series and parallel. When a single pump cannot meet the demands of a system, engineers turn to pump configurations. These configurations allow us to expand system capacity or overcome greater pressure differences. Two primary arrangements exist: series and parallel. In a series configuration, two or more pumps are placed one after the other in the flow path. The key result is that their heads, meaning the pressure gains, are additive. However, the flow rate remains the same throughout. This setup is ideal when you need to lift fluid over a tall elevation or push it through a system with high resistance.
In contrast, parallel pump configurations are used to boost the total flow rate. Here, multiple pumps work side by side, each handling a portion of the total flow. The total discharge is the sum of the individual flows. But to function properly, all pumps must deliver the same head, so their operating conditions must be matched carefully. Choosing between series and parallel depends on the system's specific needs. Do you need to overcome height, or do you need to increase the flow capacity? These arrangements allow pumps to be flexible, scalable, and responsive to changing demands. Understanding how to use them effectively is essential for designing resilient and efficient pumping systems.
7. Positive displacement pumps. Positive displacement pumps operate on a very different principle compared to dynamic pumps. Instead of imparting energy through rotating blades, they trap a fixed volume of fluid and physically move it by forcing it in or out of a sealed chamber. This gives them the unique ability to deliver a constant volume regardless of pressure fluctuations. This mechanism makes them ideal for applications where high pressure is required or where the fluid is highly viscous, such as in lubrication systems, chemical dosing, or food-grade pumping. Unlike centrifugal pumps, they don't rely on velocity but on displacement, hence the name. Common examples include rotary pumps, which use rotating elements to move fluid through chambers, gear pumps, which use meshing gears to pump fluid by displacement, and peristaltic pumps, which use a squeezing action along flexible tubing. These pumps are the go-to solution when precision, consistency, or handling thick, sticky fluids is a priority.
8. Dynamic pumps. Dynamic pumps transfer energy to the fluid using rotating impeller blades. This is not just a mechanical rotation, it's an energy transformation. The impeller adds kinetic energy to the fluid, which later gets converted to pressure energy. The direction in which the fluid exits the impeller defines the pump type. Let's break it down. Centrifugal pumps, also known as radial flow pumps, are the most common. Here, fluid is flung outward, radially, from the center of the impeller, just like how water flies off a spinning umbrella. It's ideal for high-flow, low-head applications. Next is mixed flow. Think of it as a hybrid between centrifugal and axial. The fluid exits at an angle, somewhere between the radial and axial direction. It combines the benefits of both flow types, better head than axial, and higher flow than radial. Finally, axial flow pumps push fluid straight along the shaft axis. It's like a fan pushing air forward. These pumps excel at moving large volumes at low pressure. So when you select a dynamic pump, you're really choosing the path the fluid takes, radial, axial, or a mix of both. Each has its strengths, depending on the engineering need.
9. Centrifugal pumps. Centrifugal pumps are the backbone of dynamic fluid systems. The fluid enters axially, flowing straight into the center of the rotating impeller. From there, it's accelerated outward by centrifugal force and exits radially into the pump casing, often shaped as a volute, to collect and direct the flow toward the discharge pipe. This radial movement of fluid is what gives the centrifugal pump its name. One of the most defining aspects of a centrifugal pump's performance lies in its impeller blade geometry. Blade shape affects not only how energy is transferred to the fluid, but also how efficiently the pump operates and how pressure builds within it. Backward inclined blades are the most efficient design. They reduce energy losses and are the preferred choice for most general-purpose applications. Their curved shape minimizes the velocity of the fluid at the exit, which in turn reduces frictional losses. Radial blades, positioned straight outward, deliver a higher pressure rise, but at the cost of efficiency. These are typically used when compact design and pressure buildup are more important than energy savings. Forward-inclined blades are designed to provide a more constant head across a range of flow rates. However, they tend to be less efficient and are less commonly used. Their main advantage is stability in systems where demand varies significantly. Understanding the differences between these blade geometries allows engineers to make informed decisions, balancing pressure, efficiency, and operational range based on what the system truly needs.
10. Pump matching and operating points. Every pump operates within a system, and every system imposes its own requirements. The challenge lies in finding the exact balance where the pump's performance meets the system's demand. That point is called the operating point, and it's determined by the intersection of two curves, the pump performance curve and the system curve. The pump curve shows how the head changes with flow rate for a given pump. The system curve reflects the pressure required by the piping network at different flow rates based on friction losses and elevation differences. Where these two curves cross, the system and the pump are in equilibrium. But not all operating points are created equal. There is one point where the pump performs at its highest efficiency. That's the best efficiency point, or BEP. It's the sweet spot where energy is used most effectively, vibrations are minimized, and wear is reduced. Operating consistently near the BEP extends pump life, reduces maintenance, and lowers energy costs. Straying too far from this point can cause cavitation, overheating, or mechanical stress. That's why pump matching is a critical part of system design. It's not just about moving fluid, it's about doing so intelligently, sustainably, and reliably.
11. Pump scaling laws and affinity laws. Scaling a pump system doesn't just mean making it bigger or smaller. It means maintaining performance consistency while changing size, speed, or operating conditions. That's where pump scaling laws and affinity laws come in. These principles are rooted in dimensional analysis and allow engineers to predict how one pump will behave based on data from another geometrically similar pump. The affinity laws form a set of powerful proportional relationships. They relate flow rate, head, and power to changes in impeller diameter and rotational speed. These relationships are essential when you want to scale up a prototype, modify a system for different requirements, or analyze performance across different operating points. For instance, the volumetric flow rate scales with the cube of the diameter ratio and the ratio of rotational speeds. The head developed by a pump varies with the square of both the diameter and the speed ratios. And power, the most sensitive parameter, scales with the fifth power of diameter ratio and the cube of the speed ratio adjusted by fluid density. These formulas give engineers the ability to design with flexibility, optimize systems efficiently, and reduce the need for costly full-scale testing. In short, the affinity laws are a bridge between lab-scale results and real-world pump installations. They're not just mathematical curiosities, they're indispensable tools for scalable design.
12. Pump specific speed, or NSP. Let's talk about pump specific speed, or NSP. This parameter is crucial when you're selecting or designing pumps. NSP acts as a guide that helps you decide what kind of pump fits your application best by connecting the pump's shape and flow type to its speed, flow rate, and head. If you need to move fluids using a centrifugal pump, you're typically dealing with a low specific speed. This means these pumps are best for applications requiring higher head and lower flow rates, a classic choice for many industrial settings. When you need something in between, a balance of both flow and head, you turn to mixed flow pumps. These operate at moderate specific speeds and are suitable for a wide range of mid-level pumping tasks. For cases where you want very high flow rates with relatively low head, axial flow pumps are your go-to option. These pumps run at high specific speed, making them ideal for applications like flood control or circulating large volumes of water. In summary,
Understanding NSP helps you narrow down the right pump type as it directly relates pump performance characteristics to their most efficient operating regimes. By matching your pump selection to the correct specific speed range, you ensure optimal efficiency and operational reliability for your system.
13. Turbines, turning fluid energy into mechanical power. Turbines are the workhorses that convert the energy in a moving fluid into mechanical shaft power. This transformation has shaped how we harness the force of water and steam, making everything from hydroelectric dams to power stations possible. There are two main types of turbines you should know about, each designed for specific conditions. Impulse turbines, think Pelton wheels, are the kings of high head and low flow. They use fast-moving water jets to strike buckets or blades, spinning the wheel and efficiently capturing energy when water pressure is high, but volume is low. In contrast, reaction turbines, such as Francis and Kaplan types, are built for moderate to low head with large flows. Here, energy transfer is more subtle. The pressure drops across the runner itself, and both the movement and the changing pressure of the water do work as it passes through the blades. This makes reaction turbines ideal for rivers and low-head hydropower sites. To gauge the performance of a turbine, engineers look to efficiency. In simple terms, turbine efficiency is the ratio between the useful power output at the shaft and the water power input. The formula may look intimidating. Shaft power divided by the product of fluid density, gravity, flow, and head. But it simply expresses how effectively the turbine converts fluid energy into mechanical energy you can use. The next time you flip a light switch powered by hydroelectricity, remember, turbines are quietly and efficiently converting nature's flow into mechanical motion, lighting homes and fueling industries worldwide.
14. Pelton wheel, harnessing the power of water jets. Imagine using the energy in a high-speed water jet to spin a wheel. That's the core idea behind the Pelton wheel, which is a classic example of an impulse turbine. Water jets hit buckets attached to the wheel's perimeter, transferring energy and causing the wheel to rotate. This direct action is ideal for sites where water descends from great heights, turning lofty potential energy into powerful mechanical movement. To get the most power from a Pelton wheel, the runner, the rotating part, needs to move just right. There's a sweet spot. Optimum energy transfer happens when the runner's speed is about half the velocity of the water jet. Move too slow or too fast, and you lose efficiency. Get it right, and you tap into the full force of falling water, turning a torrent into useful work. The simplicity of the Pelton wheel makes it a favorite wherever high heads and low flow rates are found, from remote mountain power stations to large-scale hydroelectric plants. With nothing more than gravity-fed water and clever engineering, the Pelton wheel stands as a testament to turning nature's energy into mechanical power, efficiently and reliably.
15 reaction turbines, Francis and Kaplan unpacked. Imagine water rushing through a curved scroll case, the pressure steadily dropping as it threads each blade of the runner. That drop in pressure is the engine of a reaction turbine. The water gives up its energy right inside the wheel itself, turning pressure into torque. Now picture the Francis design. It's a hybrid between radial and axial flow, happiest in the middle ground. Moderate heads like 30 to 300 meters, moderate to large flows. The spiral casing guides the flow inward, blades shaped like twisted spoons, fixed but sculpted for peak efficiency. Shift the scene to a lowland river where the drop might be only a few meters, yet the volume is enormous. Here, the Kaplan rules. An axial flow machine, slender like a ship's propeller, blades feathered on command. Operators twist each blade from the hub to match the momentary flow and load, coaxing every last kilowatt from slow, wide rivers. Two philosophies, one principle. Pressure surrendered inside the runner,
delivering power from alpine dams to wide delta plains.
16. Affinity laws, the scaling compass for turbines. Picture a single prototype turbine spinning in the lab. Change its speed, swap its runner diameter, or move it to a new site with a different head, and you needn't start from scratch. The affinity laws are the engineer's pocket compass, simple ratios that translate every key performance number from the known to the unknown. Double the rotational speed and the flow rate doubles, while the head climbs by a factor of 4 and the power surges 8-fold. Enlarge the runner by 10% and the flow grows with the cube of the diameter, the head with the square, the power with the fifth power. These tidy relationships, power proportional to the cube of speed and fifth power of size, head proportional to the square of both, flow proportional to speed and diameter cubed, let designers leap from model to machine, from river to river, without guesswork. One set of test data can now foretell the behavior of turbines towering in Himalayan gorges or squatting in wide tropical lowlands.
17. Pump and turbine similarity, scaling laws in action. When you're scaling up a pump or turbine, you're not just making it bigger or smaller. You're navigating a complex dance of physics and design. The scaling laws are your guide, allowing you to predict performance based on how the machine has behaved at other sizes. But it's not a perfect mirror. You have to account for the subtle differences that creep in. The Reynolds number, a measure of fluid flow relative to viscosity, can shift, affecting how the fluid behaves around the blades. Roughness, too, plays a role. As surfaces change in texture with size, they interact differently with the fluid. And then there's leakage, the sneaky losses that occur as fluid finds its way through unintended paths. These factors require careful adjustments to ensure that your scaled-up or scaled-down design performs as expected. It's a delicate balance, but with a right understanding of these scaling laws, you can make the transition from prototype to production with confidence.